Well, we're all familiar with the number line as a way of picturing the real numbers, and indeed it's a very useful picture to have in mind when you're talking about real numbers. But when it comes to analysis, we need to be just a little bit more precise. We need to say exactly what properties of real numbers we're using when we're proving things, for instance. For example, supposing I give you an arbitrary bounded set of real numbers like this one, and I ask, is there a smallest closed interval that contains it? Well, to answer a question like that, we need a very specific property of the real numbers. We need the completeness axiom. And in this program, we're going to concentrate on the completeness axiom, and we're going to use it to prove that an arbitrary bounded set of real numbers like this does indeed have the smallest closed interval that contains it. Well, I've used the words closed interval, so perhaps we ought to remind ourselves what we mean by a closed interval first. Well, here's an example of a closed interval. It consists of these two endpoints, A and B, and all the real numbers in between. Here's the notation for it, and here's the symbolic definition. It consists of the set of real numbers such that A is less than or equal X is less than or equal B. That just defines all these real numbers here between A and B, including the endpoints. So, for instance, this set is not a closed interval because it's in two pieces and there's some points missing. And this set isn't a closed interval either because these circles indicate that the endpoints are missing, and that's a very important property of closed intervals, that the endpoints should be included. Well, we don't need to just know about closed intervals, we need to know about whole families of closed intervals. Supposing this one contains another closed interval underneath it, inside it, like that. And supposing that one contains yet a third. And supposing that contains another, and so on. Well, then the whole sequence of intervals we call a sequence of nested intervals. And you've probably met sequences like this already. For instance, if we use the bisection process to find root 2, we construct exactly such a sequence of nested intervals. Well, the bisection process for root 2 goes like this. We start with the interval 1, 2, because 1 squared is less than 2, and 2 squared is 4, which is bigger than 2. So root 2 must be somewhere in this interval between 1 and 2. Then we look at the midpoint, and we ask, is the midpoint squared bigger than 2? If it is, then root 2 must be somewhere in this left-hand half, and we'll take the left-hand half as the next interval in our bisection process. If, on the other hand, the midpoint squared is not bigger than 2, then root 2 must be somewhere in the right-hand half, and we'll take the right-hand half as the next interval in our bisection process. Well, 1.5 squared is 2 1/4, which is bigger than 2, so we do in fact take the left-hand half for the next interval in our bisection process. Then we look at its midpoint. Its square is in fact less than 2, so the next interval we take is the right-hand half of that interval. Then we look at its midpoint, and its square is again less than 2, so for the fourth interval we take the right-hand half of that again. And we just keep going in this way, bisecting the length at each stage and getting a sequence of intervals getting smaller and smaller. And that's the sort of sequence of nested intervals that we're going to be interested in. To go back to the beginning, we started with the interval 1, 2. Then we looked at the midpoint. Its square was bigger than 2, so for the next interval we took the left-hand half. Then we looked at the midpoint of this new interval. Its square was less than 2, so we took the right-hand half. And we continue this process. And now, although you can't see what's going on, the process is continuing indefinitely, and the intervals are getting smaller and smaller. So we've constructed a sequence of closed intervals. Each one is contained in the previous one, and each one has length half the previous one. And the whole sequence is a sequence of nested intervals. Now, the particular property of the real numbers that we're going to be interested in, the completeness axiom, it says that when you have a sequence of nested intervals whose length gets smaller, like this one does, then such a sequence contains a unique real number. There's one real number in all the elements of the sequence, and there's only one real number. And in this case, it's the real number root 2. And to emphasize this, we have a special name for a sequence of nested closed intervals like this that contains just one number. We call it a nest. Now, what we're going to do now is we're going to use the completeness axiom, and we're going to use a bisection nest like this to construct the least closed interval for an arbitrary bounded set, like the one I started off with. So let's go back and have a look at that set. Well, here it is, and it's time to be precise about exactly which points are in it. It consists of the points 1/3, 1/4, 1/5, and so on down towards 0, and the interval from 1/2 to 1, except that 1 isn't included. It's not in our set. And now we've got to look for closed intervals that contain it. Well, here's one, from -1/2 to 2. And that's a closed interval that contains the set, but it certainly isn't the smallest one, because I could slide this bracket down to 1.5, and I can slide this one up to -1/4, and I'd get a smaller closed interval that contains the set. In fact, you can imagine sliding these brackets all the way until they won't go any further. That one can go up to 0, and then it won't go any further. And this one can come down to 1. And the interval, closed interval of 0, 1, certainly contains the set. And because of the precise way I've described this set, you can probably see that it is, in fact, the smallest closed interval in this case. But what we want is a general process for constructing smallest closed intervals like this for an arbitrary set. But before we do that, there's one little technicality we want to get out of the way. You see, everything works for arbitrary unbounded sets, like this one. And then we just have to have a concept of an unbounded closed interval as well. But, well, that really is a technicality, and, well, we've tidied it up in the text. What we're going to do in this program is we're going to concentrate on nice bounded sets like this one, and we're going to prove that such a bounded set does indeed have a smallest closed interval that contains it. And for the details of the construction, I'm going to hand you over to Tim Lister.
Suppose we have an arbitrary bounded set of real numbers, and we've shown it on the real line by this shaded portion. And we don't know exactly which real numbers are in this set. Now, what do we mean by smallest closed interval that contains this set? Well, firstly, it's a closed interval alpha beta that does contain the set. And secondly, it's smallest in the sense that any other closed interval that contains the set, such as this one, will have alpha beta inside it. But why should such a smallest closed interval exist? Now, in the particular example that Colin was looking at, it was fairly obvious that the smallest closed interval was 0, 1. But for the general set, it might be that for every closed interval containing the set, we can find a smaller one. And this is not such a fanciful idea, because it's exactly what happens when we look at not the reals, but the rational numbers. Here are the rational numbers. The particular set we're going to look at is the set of rationals between 0 and root 2. And our closed intervals must all have rational endpoints. So a rational closed interval containing our set is the interval 0 to 2. A smaller rational closed interval containing the set is the interval 0 to 1.5. An even smaller rational closed interval is 0 to 1.42, and so on. We can always find smaller rational closed intervals. The trouble is that the smallest closed rational interval ought to be 0 to root 2. But that's no good, because the endpoint root 2 is not a rational. So for any rational closed interval containing the set, you can always find a smaller one containing it. So for the rationals, we can't always find a smallest closed interval containing a particular set. But for the reals, we always can find a smallest closed interval. And since the only difference between the rational and the reals is the completeness axiom, we're going to have to use this axiom to prove this property. Now, we're going to use the completeness axiom to construct a particular closed interval, alpha beta. And we use the completeness axiom twice to construct the endpoint alpha and the endpoint beta. And since the construction is the same in both cases, we'll just concentrate on the right-hand end. Now, we're going to set up a bisection sequence. And to get the first interval, we take a point out here, which is an upper bound of the set. That is, it's greater than all the elements of the set. And we can always find a point down here, which is not an upper bound of the set, because it has some elements of the set to the right of it. Now, this is the first interval of our bisection sequence. So we start bisecting, and we look at the midpoint, and we choose the next interval as follows. If the midpoint is an upper bound of the set, then we'll take the left half interval as the next interval in our bisection sequence. If the midpoint was not an upper bound, say like this, then we would take the right half interval as the next interval in our bisection sequence. So we have now two intervals in the bisection sequence, and they are both such that their right-hand endpoints are upper bounds, and their left-hand endpoints are not upper bounds of the set. And we carry on bisecting, always choosing the interval that has this property. Each interval in the sequence has the same property. The right-hand endpoint is an upper bound, but the left-hand endpoint is not an upper bound. That is, each interval straddles the end of the set. The completeness axiom tells us that this bisection nest defines exactly one real number common to all the intervals in the sequence, and that's going to be our right-hand endpoint beta. So we've constructed the right-hand endpoint beta, and in exactly the same way we can construct the left-hand endpoint alpha, and we have a closed interval alpha beta that is a likely candidate for our smallest closed interval that contains this set. Now, to show that it is the smallest closed interval, we'll have to prove two things. We'll have to show, firstly, that it does contain the set, and secondly, that it is the smallest interval that does. Well, to show the first bit, we're going to argue by contradiction. So what would it mean if alpha beta did not contain the set S? Well, it would mean a bit of the set would have to lie outside the brackets. So a bit of the set could lie to the right of beta like this, or a bit of the set could lie to the left of alpha. But since the proof is the same in either case, we'll just concentrate on the right-hand part. So let's assume then that alpha beta does not contain the set because a bit of the set lies to the right of beta. Now, we'll get our contradiction by looking at the bisection intervals of the bisection sequence that we use to construct beta. And remember that these had the property that their right-hand endpoint was an upper bound for the set. Here's the first interval. You can see the right-hand endpoint is an upper bound, the left-hand endpoint is not. Here's the next interval. But the next interval gives us the contradiction. According to the rule, the right-hand endpoint should be an upper bound. But now there's a part of the set beyond the right-hand endpoint, so it can't be an upper bound. This contradiction means that the assumption we started with in the first place is wrong. There can't be a part of the set to the right of beta. So we can't have any of the set to the right of beta, because if this was so, then we'd have some of the set to the right of one of the intervals of the bisection sequence that we use to construct beta, and this contradicts the rule for choosing these intervals. So we can't have this. Similarly, we can show that we can't have any of the set to the left of alpha, and so alpha beta contains our set. Right, now to show the second bit, we have to show that alpha beta is the smallest closed interval that contains the set, which is that if we have any other closed interval, such as this one that contains the set, then we have to show that alpha beta lies inside this interval. Again, we'll argue by contradiction. So what do we mean by alpha beta not lying inside another closed interval containing the set? Well, we'd have to have this right-hand endpoint strictly to the left of beta, and since our interval contains a set, it would be something like this. Or we could have the left-hand endpoint to the right of alpha, but to be definite, we'll just concentrate on this right-hand end. So we'll assume that we have another closed interval containing the set, which is such that its right-hand endpoint is strictly to the left of beta. And we'll get our contradiction by again looking at the intervals of the bisection nest that we use to construct beta. And remember that the rule for choosing these intervals said that their left-hand endpoint were not upper bounds of the set. Here's the first interval. Remember, its left-hand endpoint is not an upper bound. Here's the next interval. And the next. But for the next interval, the left-hand endpoint is an upper bound because the set doesn't reach it. And there's our contradiction. So we can't have a definite gap between the set and beta, because then we'd have one of the intervals of the bisection sequence that we use to construct beta having its left-hand endpoint in this gap. And that would contradict the rule which we use to choose these intervals. So we can't have this gap, so it must be like this. Which means that any other closed interval that contains the set can't have its right-hand endpoint down here. It must be greater than or equal to beta. And in a similar way, we can show that the left-hand endpoint would have to be less than or equal to alpha. So for any other closed interval that contains a set, we have alpha beta inside it. Well, that's our theorem then. We have constructed alpha beta, and we have shown that it is the smallest closed interval that contains a set, and we can do this for any set of real numbers.
So we've proved our theorem. But there is just one point that I'd like to draw to your attention. This right-hand endpoint, beta, it's an upper bound for the set. And what we've just proved is that it's the least upper bound. And in a similar way, the other endpoint, alpha, is the greatest lower bound for the set. So another way of thinking of this least closed interval is it consists of the least upper bound and the greatest lower bound for the set. But the most important idea in this program was this idea of a bisection process being used to construct particular real numbers. And it's a very important process, and we'll see it again many times in analysis. In particular, in the third analysis unit, we'll use it to prove some important properties of continuous functions.